नहीं नहीं ना, शो नहीं करना। Okay, everyone. Assalamu alaikum. I hope you guys are all doing well. Let's begin with our next topic today, which is integration. So we're starting P3 integration today. We're done with differentiation. We did a lot of practice questions on differentiation yesterday. If you did not attend that class, please make sure to watch the recording and look at the notes so that you can see all the questions that we attempted in that class. Okay. Some of them were quite difficult, quite complicated. So you need to make sure that you understand the concepts that we covered in them. So now we are starting our next topic, which is considered to be the most difficult topic of paper 3, and sometimes of the whole A-level. But if you understand the concepts well, you will find yourself finding it not that difficult, because once you understand, once you remember all the rules that you have, it kind of starts getting repetitive at some point, that just by looking at the function, you can see how you're going to integrate that, but that comes with practice. So we'll try to do a lot of practice in order to get to that level that you can start feeling comfortable looking at integration questions. So let's start with this. Now, first of all, as with other P3 topics like trigonometry and differentiation, there are some concepts that you've done in paper 1 already, and it's necessary for you to remember those concepts that you've done in paper 1. So let me quickly remind you about what you need to know from P1 integration. So what have you done in P1 integration? You've basically looked at this particular rule in paper 1, power rule, ax plus b whole raised to power n. What's the integral of that? It's ax plus b whole raised to power n plus 1 over a into n plus 1. So basically we add 1 to the power, divide by that new power, and divide by the derivative of the base of the power. These three things we do when we integrate power functions. That's the only rule that you've done in paper 1, the power rule of integration. Now, there was a condition for this rule, and that condition was that the part inside the integral that had to be linear. If it was not linear, then you could not use this rule. All right, so this part had to be linear. That was necessary. If it was not linear, for example, if it was something like this, 3x squared plus 2 whole squared, if you had something like this, how would you integrate this? The part inside is not linear. You would first have to expand it and then integrate it, right? This is something that you should know from paper 1. This was the only rule of integration that you did in P1. All the other rules of integration, of integrating a number of other types of functions, you will do in paper 3. However, there were some applications of integration that you did in paper 1 that are still going to be relevant here. What were those applications? You would have the derivative of a function given sometimes, and you will be asked to find the equation of the curve, equation of the function. You'll have to integrate it, have a plus c with that, and find the value of plus c using a point that is given, right? So that is still going to be used here. And then you would have to find areas between graphs and x-axis. This is the formula that we have for that, integral of y with respect to x, right? And then area between a graph and y-axis, this is the formula that we have for that, integral of x with respect to y. And then if you have to find area between two graphs, for that you find area between one graph and the x-axis and find the area between the other graph and the x-axis, find their difference, and that gives you area between two graphs. Then you've done volume of revolution. How to find volume of revolution between a graph when the area between a graph and x-axis is rotated about x-axis. This is the formula that you have for that: pi into integral of y squared with respect to x with limits of x, right? And then you have volume of revolution about y-axis. That's this formula: pi into integral of x squared with respect to y. In this case, x squared should be the subject and limits should be of y. And similarly, if you have to find volume of revolution of the area between two graphs, you have to find the volume of revolution for one of them, subtract from that the other one, you get that volume. So all of these concepts you've done in paper one, and also sometimes when you get infinity as one of the limits, right? Sometimes that also happens. It happens more so in paper three. You will have infinity as one of the limits sometimes. How to deal with that, right? When you input infinity, if it comes in the denominator, that fraction becomes zero. This is also something that you've done in paper one. So all of these concepts, they are still relevant for paper three, all right? You need to remember those concepts. If you think you need to revise any of that, make sure that you do that as soon as possible. Don't delay that, because we will have to do that in the questions that we do on paper three now. So now what do we have in paper three? All of those applications of paper one are still relevant in paper three. So what is new? The new thing is how to integrate other kinds of functions. Just like in differentiation, in paper one, we learned how to use the power rule. And in paper three, we learned how to differentiate sine, cos, tan, secant, cosecant, cot, and then how to differentiate products, how to differentiate fractions, how to do implicit differentiation when y was not the subject, how to do parametric differentiation. We learned all of that in paper three. Similarly here as well, we will learn how to integrate a number of different types of functions. And they're just quite a large number of different types of functions that you have here. So you need to make sure that you start remembering what form is integrated using what form, what rule. So that is something that you have to start from today. Start remembering, okay, for these functions, you have to use these rules. For such kinds of function, you have to use this rule. So you need to remember all of that. Now, first of all, we're going to start with some very simple functions. Now, I've taken this from the formula sheet. This is given in the formula sheet. So if you look at the formula sheet for integration, these are some of the rules that are given. Now, there are some things that you need to know apart from this as well. But I'm going to start with some of these that you can integrate directly. For example, x raised to power n, you've done this in paper one already. I showed that to you as well. But then you have some other functions which can be integrated directly. There's no complication there as such. We're going to start with that, how to integrate these functions, and then we'll build on that after that. So first of all, we have x raised to power n. That's a power function. How do you integrate power functions? Add 1 to the power, divide by that new power. But this is the form that's given in the formula sheet. What if you had, in place of x raised to power n, what if you had something else raised to power n? So what you can have here is some linear expression. So let me write that down. The general form for this that you need to understand. If you have ax plus b whole raised to power n, some linear expression, so the part inside the power, that has to be linear. So this x here can be replaced with some other linear expression. So in this case, it could be ax plus b, for instance. What would be the integral for that? Integral of that would be ax plus b whole raised to power n plus 1. You add 1 to the power, divide that by that new power, and also divide by the derivative of what is inside the power, that's a, you divide by a. That's what the rule becomes. So it's the opposite of differentiation. Differentiation, we used to multiply with the derivative of what is inside. Here we divide by the derivative of that. However, in integration, we have a condition that this part inside, it has to be linear. If it's not linear, then you can't integrate it using these rules. Okay, then we'll see what to do after, later on. But in order to use these rules directly, the part inside has to be linear. That's important. Now, the next function is e raised to power x. How do you integrate e raised to power x? In place of e raised to power, in place of x, you could have something linear. So you could have e raised to power ax plus b, for instance. How would you integrate that? Now, remember the derivative of e power x, the derivative of e power x was e power x. So the integral of e power x is also e power x, all right? However, if you have some other expression, if x is replaced by something else, if you have e raised to power ax plus b, how do you integrate that? The rule is e power x stays e power x, so e power ax plus b stays e power ax plus b. However, whatever you have in place of x, you have to divide by the derivative of that, whatever linear expression you have. So in this case, it's ax plus b, you'll have to divide by a. That's the rule that we have for e power ax plus b. And then similarly, you have the other rules here. Integral of sine is minus cos, of cos is sine, and of secant square it's tan. So remember, the derivative of sine was cos, so the integral of cos is sine. Derivative of cos was minus sine, so integral of sine is minus cos. Derivative of tan was secant square, integral of secant square is tan. So it's just the opposite of differentiation. That's all that is happening. Now you could generalize these rules as well like this. So just like we had for the power function, this is for the exponential function. And then for sine, you could say if you had sine of ax plus b, integral of that would be minus cos of ax plus b divided by a. And similarly for cos, you have cos of ax plus b, integral of that would be sine of ax plus b divided by a. And then finally, you could have secant square of ax plus b. The integral of that would be tan of ax plus b divided by a. These are some rules that you can use directly from the formula sheet. There's not a lot of thinking involved here. You just use the rule as given in the formula sheet. Okay, let's take an example. Let's say you have something like this. I'm going to leave some space here because I want to add something to that space in a moment. Let's take an example. Let's say we have minus 4 e raised to power 3x. We want to integrate this with respect to x. What's the integral of this? Now, the constant remains as it is. The constant does not change. The constant that's multiplying, that remains as it is. So this constant is multiplying, that remains as it is. What's the integral of e raised to power 3x? Integration of e power x is e power x. So integration of e power 3x is e power 3x. However, we have to divide by the derivative of whatever is coming in place of x. So we have 3x in place of x. We divide by the derivative of that. So it's e power 3x divided by 3 plus c. That's the integration of this thing. All right, let's take another example. Let's say you have 4 over 3 into secant squared of minus 2x plus 5. You want to integrate this with respect to x. Now, 4 over 3 is a constant. That remains as it is. The 4 over 3, the constant that's multiplying, that remains as it is. What is the integration of secant square? Well, we know from the formula sheet, the integration of secant square is tan. So this converts to tan. It becomes tan of 2x plus, sorry, tan of minus 2x plus 5. All right, but then whatever is inside here, so the rule said, if you have secant square x, the integral of that is tan x. But if you have something other than x, then you have to divide by the derivative of that as well. What's the derivative of minus 2x plus 5? Minus 2, you divide by that. And then you can simplify this 4 over minus 2. That's going to be minus 2 over 3 into tan of minus 2x plus 5 plus c. That's the integral of this expression. Now, in this original rule as well, there is division by the derivative. But what's the derivative of x? The derivative of x is 1. So it doesn't matter if we have 1 there or not. Division by 1, it's not going to change anything. So with all of them, we are basically dividing by 1 because the derivative of x is 1. But if you have something other than x, then the derivative would not be 1. So you would have to make sure that you do that division there. all right? However, the condition is the part inside, the part in place of x can only be something linear. And we discussed the reason for this in paper 1. Basically, if you have something quadratic, if you have x squared, or let's say you had sine of x squared plus 2, if you were to apply that rule here, it would become minus cos of x squared plus 2, and you would have to divide by 2x. X is a variable. A variable can have a value of 0 as well. So if it becomes 0, this whole function would become undefined. So division by x, we have to be wary of that, as in we don't generally divide by x because the value of x could also be 0, and that will make this function undefined. So division by x is something that we avoid. So this rule cannot work like this. When you have a linear expression, the derivative that you divide by, that is a constant. So we are not dividing by x there. So that does not cause that problem. Okay. So that's the reason, but you need to remember this now. In the formulas, in these rules, x can be replaced by something linear, not by something non-linear. Okay. Now let's do another example. Let's say you have something like this: integral of 3 into cos of 4x squared plus 1 with respect to x. What will be the integral of that? Quickly, what's the integral of that? Anyone? Just a quick test on what you've learned.
3 sine 4x square plus 1
3
upon
sine of 4x squared
8x
plus 1 over 8x.
8x बट आपने ये कहा हम डिनोमिनेटर में x नहीं लिख सकते so
So
we're
this
gonna
doesn't work,
multiply
right? So we can't do this. This is not going to come. This is non-linear. In order to integrate this, they will give you something, some other information. We will see later. You can't integrate this function directly, but if you had x outside multiplying as well, then you could do it. But for that, they will give you a substitution to use, which we'll learn later. But this is not linear. So remember not to apply this rule here. Okay, you cannot apply this rule. That was just the point that I wanted to make here. If it's not linear, don't use this rule. It's not going to be correct. All right, is that okay? Any problem with this? Okay, so these are some rules that you can use directly from the formula sheet. All right. Now, in addition to these rules, there's something that has actually just started happening this very year. In fact, the last year, 2023, I was doing a question with some other students in the recent paper. And now the examiner basically expects you to know 3 other integrations as well, which are not given in the formula sheet. They're not given in the formula sheet anywhere here. But remember, in differentiation, we did 3 other differentiations as well. So on the differentiation page, you had a function secant x, you had another function cosecant x, you had another function cot x, and we had their derivatives given. The derivative of secant x was secant x tan x. The derivative of cosecant was minus cosecant cot. The derivative of cot was minus cosecant square. These are given in the differentiation formula sheet, right? On that page, on the differentiation page, you have these 3 rules given. We discussed these 3 rules in differentiation, but they're not given in the integration, on the integration page. But the examiner still expects you to be able to use them. Now, what does that mean? Let me just copy this here. These are the 3 differentiation rules that you have, okay? Now let's have them in front here. So you will have the differentiation formula sheet with you. These are the rules that are given in the differentiation formula sheet. From these 3 rules, you can make 3 other integration rules. And they look like this. If you have a function which is secant x into tan x, what would be the integral of that? Derivative of secant x is secant x tan x. integration of secant x tan x would be secant x, right? Integration is just the opposite of differentiation. So if you have secant x into tan x, the integral of that is secant x, all right? Similarly, if you have cosecant x into cot x, integral of that is minus cosecant x, all right? So this is negative, so we also put a negative when we're doing integration. This is minus cosecant x. And then finally, if you have cosecant square x, the integral of that is minus cot x. All right. These are three rules that are not given on the integration page, but the examiner expects you to know them. They are given in the differentiation sheet. You just have to reverse them. Now, once you reverse them, it also means if you had, for instance, a function like this here, if you had secant of some linear expression into tan of some linear expression, what would that become? Secant of ax plus b divided by a. So you could use that rule the same way here as well. This is the rule that you understand from the differentiation formula sheet. In place of x, if you have anything else, you just divide by the derivative of that thing as well. The rest of the rule works the same way as before. Okay. Similarly here, if we have cosecant of some linear expression into cot of some linear expression of that same linear expression, they have to be the same. They can't be different. So this and this, they have to be the same. They can't be different. Okay. That's important. That is going to become minus cosecant of ax plus b. And then finally, if you have cosecant square of ax plus b, integral of that is minus cot of ax plus b divided by a. These are three new rules that you have that you also need to be able to use. Does this make sense to everyone? Now, let me actually show you that example that I'm talking about that actually came in June 2023 exam. Let me see if I can find that. Yeah, so this is what came in that exam. Let's show that to you quickly. Let me move on to the next rule after this. Integral of 4 tan of 2x divided by cos of 2x. So examiner expected you to integrate this. It was part of a differential equation question, but while solving that, you had to integrate this thing. Now, there's no way to integrate this unless you know these rules, or you'll have to figure out these rules yourself, right? That is possible, as in to derive these rules yourself, but it's very improbable that we'll be able to do that in the limited time that you have during the exam, right? So maybe outside the exam, you could figure it out yourself, but during the exam, you have to use that rule now. Otherwise, you can't figure this out. 4 tan 2x divided by cos of 2x. What we actually can do is we can write this as 4 tan of 2x. Cos is the reciprocal of secant, or secant is the reciprocal of cos. So this cos, we could bring this to the numerator, and that will become secant of 2x. And now we have 4 into tan of 2x into secant of 2x. If you rearrange this, that gives you 4 into secant of 2x into tan of 2x. And that should remind you of something. Secant and tan, when they're multiplying, this is the form that you have, right? Secant x tan x. Similarly, you also need to remember this. If you had this form, make sure that reminds you of this formula, look at the formula sheet and see that, okay, this could be used, right? So in this case, it becomes secant 2x into tan 2x. Now, what's the rule? The rule is integral of secant x into tan x with respect to x, which you can figure out from the differentiation worksheet, differentiation formula sheet. This is the rule that you can get for integration. But here we have 2x instead of x. So what we do is we divide by the derivative of 2x, which is 2. So the integral becomes something like this. 4 into integral of this thing is secant. So that's secant of 2x divided by 2. And that leaves you with 2 secant of 2x plus c. That's the result that we get from this. So that is how you could use these 3 other rules that you have. You need to keep them in mind as well. They're not on the page where we have the integration rules written. They're on the page where the differentiation rules are written. You can reverse them to make your own integration rules like this. Any problem with this?
Sir, we had no other way, like if we converted tan into sine over cos.
No, you can't do that. You can try doing that. Sine 2x divided by cos square 2x. What do you do after that? It doesn't become any of the standard forms. It's not the ln form. It's not the tan inverse form. You can't do partial fractions. So none of those rules for partial fractions work here. You could try making it a product and do integration by parts, but that also doesn't work because it doesn't simplify. So no. As in, there would be a way, but it'd be extremely long. You can't do that in an exam. All right. So integrating this was actually just 2 marks in this part. So it was a 6-7 mark differential equation question. Integrating this part was 2 marks. So if you were to try something else, that's going to take like too long. Okay, for 2 marks. So you have to now know these 3 rules as well. Okay. Any problem with this? No? Okay, now let's move on to the next one. Now the next rule that we want to do is the ln rule. Now this is the most commonly used rule in P3 integration. Almost in every other question, you will need to use this, the ln rule. Now, what does this mean? Now, in the formula sheet, you basically have 2 different forms written for this. First of all, in fact, there are 4 in total. First of all, you will see something like this in the formula sheet. If you have 1 over x, what's the integral of that? That is ln of x. Remember, the derivative of ln x was 1 over x. So what's the integral of 1 over x? It's ln x, all right? So that's how you can do integration. This is one rule. So this could be used, for instance, if you had integral of, let's say, minus 4 over x with respect to x. If you had to integrate this, you could say minus 4 is a constant that's multiplying. You could write this outside the integral. So that it becomes minus 4 into integral of 1 over x with respect to x. 1 over x can be integrated as ln x. So it's minus 4 into ln x plus c. That's the integral that you get from this. All right. This is a very simple example of ln. Remember, the power rule cannot work here. Can you use the power rule here? Will that work? Okay, minus 4 over x. Minus 4 over x. How do you integrate this? Minus 4x raised to power minus 1. If you were to try using this, doing this using the power rule, it would not work. Why? Because it becomes x raised to power minus 1 plus 1. When you add 1 to the power becomes 0. Then you divide by 0. That does not work. It becomes undefined. So when you have x raised to power minus 1, the power rule does not work there. So you have to use this ln rule instead. Okay. Now this is a very simple case of when you get ln. However, we have a more general rule for ln as well. Let's look at that, and that's what we will mostly be using. Now for that, let me first remind you of what you have done in differentiation earlier. Remember how you used to differentiate expressions like this? If you had y equals ln of maybe 3x squared minus 1, if you had to differentiate this, how would you do that? The derivative of ln of something was 1 over that thing, right? So you would say 1 over 3x squared minus 1, and then you would multiply by the derivative of this thing. What's the derivative of this? 6x. So it becomes 6x over 3x squared minus 1. So in general, the rule was that if we have y equals ln of something, ln of anything, remember in differentiation, we did not have that linearity condition that was not there in the differentiation rules. In differentiation, you could have anything inside. In integration, we want that thing to be linear generally in order to use these earlier rules that we have discussed. For this, in place of x, you can only have something linear. But remember the general rule that we had for log there, for ln there, what was the rule? ln of something, the derivative of that was 1 over that thing, and then multiply by the derivative of that thing. And that used to give you something like this. That you had an expression in the denominator, and in the numerator, you had the derivative of that. All right. That's what used to work in differentiation. Now, since integration is the opposite of differentiation, you can say if you have a fraction of this form, what form? You have an expression in the numerator. Now it could be any expression. If that is the derivative of the denominator, if numerator is the derivative of the denominator, what is the integration of that going to be? Integration is going to be ln of the denominator. This is the rule that you have for integration. It's written in the formula sheet in this manner. I'm going to write this for you. So you have that in the you have that reference from the formula sheet as well. It's written like this in the formula sheet. The formula sheet says f dash of x divided by f of x, integration of that, integral of this, that is ln of f of x. That's the rule that is given in the formula sheet. You can see that here. This is the integration page of the formula sheet. This is what I'm talking about. The last thing that's written on this page is this: f dash of x over f of x, integral of that is given by ln of f of x. Okay. Now, in words, we could remember it like this. Now, this is the form that we have. You can kind of remember it this way. You can say if numerator, if you have a fraction such that numerator is the derivative of the denominator. If you have a fraction such that the numerator is the derivative of the denominator, and you were to integrate that, integral of that is going to be ln of the denominator. Now they've used the modulus sign here. That's what the formula sheet does for wherever it has ln, because log cannot have anything negative inside, right? Log will be undefined if you end up getting something negative inside. That's why they use this modulus sign here. Because of that, it's not necessary that you write them. It's better to write this in modulus form. But even if you don't do that, they don't deduct marks for that. But they prefer that you write this modulus form when you have ln of something. All right. But it's your choice at the end of the day. So that's the rule that we have. Whenever you have a fraction in which numerator is the derivative of the denominator, whenever you have a fraction in which numerator is the derivative of the denominator, the integral of that is ln of the denominator. That's what the rule says. Okay? Integral is ln of the denominator. Make sense? Now we have a number of different rules for fractions. This is the first rule that we're doing now. You need to start remembering them as well. Start kind of learning them, as in remember them. What rule works in which scenario? What's the condition for that? And that is what is going to help you solve different integration problems, because the key problem in most persons is figuring out what method to use, because there are so many different methods. So you need to understand what method works in which case. So when numerator is the derivative of the denominator, what do? The integral is the ln of the denominator. All right. Now let's look at some examples of this. Let's say you have a fraction that looks like this. 2 over 2x plus 1. You want to integrate this. How do you integrate this? 2 over 2x plus 1. What's the integral of this? You see, this is that form. What's the derivative of 2x plus 1? Derivative of 2x plus 1 is 2. So numerator is the derivative of the denominator. That condition is satisfied. Right? This condition is satisfied. So what's the integral then? What's the integration of this? Integration of this is going to be ln of the denominator, ln of 2x plus 1 plus c. All right. That's the integration of this fraction, because it's of that form. Numerator is the derivative of the denominator. Now let's take another example. Let's say you have something like this. Integral of a fraction that looks like this, minus 8x plus 3. And in the denominator, you have minus 4x squared plus 3x minus 10. You want to integrate this. What's the integral of this thing? It's a fraction again. You have only done one rule for fractions until now. There are a number of other rules as well, which we will be doing in the next couple of classes. This is the first rule and the most important one, because it's the most commonly used one. Minus 8x plus 3 over minus 4x squared plus 3x minus 10. How do you integrate this? Does this satisfy that condition as well? What's the derivative of the denominator? The derivative of the denominator is minus 8x plus 3. So that condition is satisfied. Numerator is the derivative of the denominator. So what do we say? Integral of this is going to be ln of the denominator, which is minus 4x squared plus 3x minus 10. That's the integration of this fraction. Does that make sense? Any issues until this point? No? All right. Now, in both of these examples, we already had that form, as in we did not have to change anything to that fraction, change anything in that fraction to make it the form that we need. It was already that form. All right. Now, a lot of times what happens is you have to change something in that fraction slightly to make it this form that the numerator becomes the derivative of the denominator. Let's take an example. Let's say you have minus 4 over 2x plus 7. You want to integrate this. Now, what about this? Does this satisfy that condition? Is numerator the derivative of the denominator? What's the derivative of the denominator? Derivative of denominator is 2. The derivative of 2x plus 7 is 2. You don't have 2 in the numerator. You have minus 4 instead. But can you have 2 in the numerator somehow? What you can do is you can say, let's take 2 common from the numerator. Minus 2 common, in fact. So it becomes minus 2 into 2 divided by 2x plus 7. You take 2 common, minus 2 common. And now minus 2 is just a constant. You could write minus 2 outside the integral as well, right? If a constant is multiplying with the whole thing, you can write it outside the integral as well. So we could write this same thing as minus 2 into integral of 2 over 2x plus 7. And now the part inside the integral follows that condition. Numerator is the derivative of the denominator. All right. Now you could jump from this step to this step directly. It's not necessary for you to show this. I've just done this for making sure that you understand what we're doing exactly. This was a constant. We can just write that outside like this. Now this form is that form. Numerator is the derivative of the denominator. So what does the integral become? It becomes minus 2 into ln of 2x plus 7 plus c. That is the result that you get from this. Make sense? Okay, let's take another example. Let's say instead of this, you had something like this, 7 over 4x minus 1 with respect to x. Let's say we had to integrate this thing. Now, can we use this rule here? 7 over 4x minus 7, 4x minus 1. What do we want in the numerator? The derivative of the denominator is 4. If we can have 4 in the numerator somehow, we could apply that rule. But we have 7 right now. Can we take anything common from 7 to make it 4? Well, we'll have to take something common in decimals. That's going to make things complicated. So how we think about this is this. We say 7 is a constant. Let's just write 7 outside. Right? We can do that. 7 is multiplying with the whole thing. We just write that outside. And inside we're left with 1 over 4x minus 1. All right. So we've just written 7 outside. Now, what do we want inside? In the numerator, we want 4. So what we do is we say, let's multiply by 4 and also divide by 4. Now, the 4 that you have in the denominator, you say, instead of writing this inside, we could write this outside as well. That's just a constant. It doesn't matter if we write it inside or outside. So we multiply by 4 inside and we divide by 4 outside. Now, the expression inside the integral follows that condition. Numerator is the derivative of the denominator. So the result is going to be 7 over 4 into ln of 4x minus 1. That is the integral that you get from this. Make sense? So sometimes the actual form, the given form is not the standard form, where the numerator is not the derivative of the denominator in that form. What we have to do instead is we have to multiply or divide by a constant like this to convert to that form first. Does this make sense? Any quick questions on this? No? Okay, let's take another example. Let's say we have something like this. In the denominator, let's say we had 5x squared minus 8x plus 13. And the numerator, we had 5x minus 4. And we wanted to integrate this with respect to x. How would you do that? Can that ln rule be used here? Let's think about it. What's the derivative of the denominator? The derivative of the denominator is 10x minus 8. Can we have 10x minus 8 in the numerator somehow? Is that possible?
Multiply and divide by 2.
Multiply by 2, right? So in the numerator, if you were to multiply by 2, what is this going to become? 5x minus 4 multiplied by 2 outside the integral divided by 2. So you have 5x squared minus 8x plus 13 in the denominator like this. Okay. And now the part inside follows that rule, follows that condition. Numerator is now the derivative of the denominator. Okay. So we multiply by 2 inside, divide by 2 outside, and that gives us that form. And now we can say the integral is 1 over 2 outside remains as it is. The part inside integrates to ln of 5x squared minus 8x plus 13 plus c. That is the integral that you get from this. Make sense? No problems? Okay. All right, good. Let's have a look at one more example and maybe 2 more examples. Let's say we have something like this. Let's consider the same example. And now let's say we had 5x plus 4 here. How do we integrate this? What about this now? What's the derivative of the denominator? Derivative of denominator is 10x minus 4, 10x minus 8, sorry. Can we have 10x minus 8 in the numerator somehow? Can we have 10x minus 8? We can't, right? So this is something that we cannot integrate using this ln rule. This can't be integrated like this. Okay. Now we might see later if we can do it some other way. Although in this case, the denominator can be factorized or not. No, it can't be factorized. So yeah, so there is not much that we can do with it. The ln rule does not work. So it's not going to work on every single fraction. Sometimes it's going to work. Sometimes it's not going to work. Sometimes you'll have some other method of doing this. Sometimes you won't have any method. In that case, it won't come if it doesn't have any method. So if the ln case does not work, you would do it some other way generally. All right. But in this case, the rule does not work. Okay. Let's take another example. Let's say you have something like this. You have 2 over x squared plus 9. Let's say you wanted to integrate this thing with respect to x. How do you do that? Can this be done? 2 over x squared plus 9. How do you integrate this?
Multiply by x.
Multiply by x, right? So in the denominator, we have x squared plus 9. What's the derivative of x squared plus 9? Is 2x. So in the numerator, we want 2x. So we might think that we multiply by x and divide by x, right? So we actually do it in the next step. We might think of doing this 2 over x squared plus 9 into x and then divide by x. But this is not going to work. This is not going to work. Okay. Now, why does this not work? There are 2 reasons for this. One, you're dividing by x. If you're dividing by x yourself, that's a problem, right? We discussed this earlier as well. Division, x could be 0 as well, then you have a problem. So we generally avoid dividing by x ourselves. Okay. And the second thing is, when we are multiplying by x inside, x is supposed to be divided inside as well in this case. Earlier, we had a constant. We had 2 over 2 inside. Constant can be written outside and it would not make any difference. You can't write x outside. You can't say that this x can be written outside the integral. In that case, you could say, if you have integral of x with respect to x, you could say, I can just write x outside. That doesn't make sense, right? X cannot be written outside the integral. Only constant can be written outside the integral. So this is not going to work. You can't do this. In this case as well, ln rule does not work. Okay? So what you need to remember is you can only multiply or divide by a constant, not a variable, not by x. Okay? In order to convert to that form, you can only multiply and divide by a constant. You can't do multiplication and division by a variable. Okay? Not by x. Is that okay? And we will see later, this will actually be done using another rule. ln rule does not work here. We'll have to use another rule for this, which we'll discuss tomorrow, inshallah. Now, this is the next exercise for you. We will discuss these tomorrow. These functions tan x, and let's say you have cot of 3x, they are also integrated using the ln rule. Think about this, how the ln rule can work here, because ln rule works on fractions, right? How does it work on tan x and cot of 3x? Think about this. We'll discuss it in the next class. If you have any quick questions on what we have done until now, let me know. Otherwise, we're going to end this here, and I'll see you tomorrow. Any quick questions, anyone? Any problems? No? Please try this for tomorrow. Tan x and cot of 3x. Think of how the ln rule, the rule that we've just discussed, could work on these two examples. And this is something that you need to remember then, that tan x can be integrated using the ln rule, cot of 3x can be integrated using the ln rule. But we will discuss this in more detail tomorrow then. All right, that's it for today. I'll see you again in the next class. Allah Hafiz, everyone. Bye.
Allah.
Allah Hafiz.